Welcome to another Silicon Valley history talk. And this time we have with us here Jack Boyd, who is a longtime professional of NASA. He's been in many positions at the NASA Ames Research Center, to which he came to work in 1947. A long history is behind him. The reason I'm especially excited about this talk today is that sometimes, we lose track of all the important people that run systems. We at Google have a large SRE group, which is, not so known outside of Google, but which does a very serious job of running everything we do here. I would dare to say that NASA Ames Research Center did such a serious job for the NASA program as a whole. Some of the things they've done through the history, of which we will hear today, have made actually the space program possible. And without it, I doubt that a lot of accomplishments would have been made, especially during the lunar years and even during the shuttle years. So please welcome Jack Boyd here and give him a warm welcome.
And thank you very much. Can you all hear me? Okay. I'll start off by saying that I was also, having been with NASA for many, many years, I was also at the University of Texas for some time as a chancellor for research. And while there, Ann Richards was governor. You've probably heard of Ann Richards. And she used to say a good talk in Texas was called a Longhorn. It had two good points, a long way apart, with a lot of bull in between. So there will be some bull, I'm sure, but there's some good points to be made here. I'm going to go quickly through some of the past 100 years of aerospace and then the Ames part that we played in it. First chart. This one I want you to kind of look at. I'm always struck by this. You can glance at these icons and see what they are, but from 1900, when the Zeppelin first flew, to the first supersonic flight by Chuck Yeager was only 47 years. 47 years. It was only 69 years from that time to the first lunar landing. 69 years. Now, look over here here. 69 we landed. How many years before we go back? More than 50. I doubt 49 is right anymore, but it'll be a long, long time. We seem to have lost the knack somehow, unlike Google, of doing things fast, accurately, and at cost. That's another problem we're having. But that's just some thoughts of the last 120 years. The next chart, we'll get into a little bit. These are just another set of icons. I wanted to comment on a few of them. We weren't here when this started, but we were soon thereafter here. And we've covered most of this spectrum of 50 years with NASA. Those are many of the things we've done, and I'm going to touch on them a little more accurately, or a little more in detail before we're finished. But what I really want to focus on as we go through it is the contributions these people made from this little center, which is next door to you, over the past 70 years. Incidentally, this December will be our 70th anniversary. I've been there for 63 of them, so I've seen it change a lot. The next chart kind of gives you, this is before even I got here. This big hangar that you see, which we're hoping to replenish, the Navy built it, of course, many years ago for the Macon. And it's now, we've discovered it has contaminants in the surface, so we're going to have to fix it some way. The Navy will deskin it. Who's going to reskin it is the debate we're having right now. So that comes later, but we hope to use that again someday. And the next chart shows something I like. This Macon, I'm an aero engineer by training, and I was intrigued by the fact that it housed inside its structure, and it's a rigid airship, remember, like Zeppelins are, 6 of these little vehicles. And they would actually come up and hook on, be sucked up inside. They'd send them out again on scouting missions. So they would release from that part right there, and come back and hook onto it, very slow. The Zeppelin would go very slow, of course. They would come up and hook onto it. That was going on in the 30s, just before now NACA formed Ames out here. And the next chart shows us a groundbreaking. This is December 20th, 1939. Long, long before your folks were born, who started Google. I was born, but I was not thinking about coming to California in those days. I lived in Virginia. This gentleman right here on the far right that you see became one of our stalwarts, but he was the NACA person who came out to help us break ground. And the next chart shows kind of a little bit about the various laboratories. NACA, which you may not have ever heard of, was called the National Advisory Committee for Aeronautics. Started in 1915. I think it was the same year that Einstein formed his general theory of relativity, so it was a pretty good year. And the first center was Langley Field in Virginia, the first Aeronautical Research Center. They were the ones who started this whole business. In the mid-30s, Charles Lindbergh, he played a big part in Ames, it turns out, for several reasons. Decided, after visiting Germany many times, that we were in real trouble in the aeronautical research world, and we needed a second center. And the president said, okay, if you think we need a second center, go find where we should put it. Well, East Coast, we had one, Langley Field in Virginia. He got as far away from Langley Field as he could find. It was a Navy base here, so in 1939, he picked this site named after this gentleman here, who is, Ames was the president of Johns Hopkins University and a member of NACA. NACA ran the 4 centers you see here. Lewis, which is now called Glenn in Cleveland, was the next center, and Dryden in the desert in 46. That was the core of NACA. That's what formed NASA. All we did in those days was low-speed, high-speed aero research. When we became NASA, things changed quite abruptly. Next chart. I say played a part. This is our first director, our first associate director, and Charles Lindbergh in the lobby at the building 200, if you've ever been over to Ames, having their picture taken. He came out here a number of times, and just an aside, many years later, you've heard of Sophia, the high-flying 747 aircraft we're going to do infrared astronomy on. We got that from United about 10, 12 years ago. Turned out it was an Ann Morrow Lindbergh Clipper, which was on the front of it. So we're going to replace that on it. So Lindbergh's family has been connected with us for many years. The next chart, I thought this would be kind of funny. NACA computers. These are our computers. When I came out here and got data out of wind tunnels, we'd turn it over to these young ladies who had IBM calculators. And if you've ever heard, these days you say someone married their computer, is married to. Many times we married the computers, you know. Some of the engineers actually took us up. I did not, but many of my friends married the young ladies who did the data reductions for us. And that was back in the 40, 41, 42 era. Now we got, as you know, the next chart, the new computer we've got here, not so enchanting, not so endearing, but very effective, very efficient. That's the newest computer we've got at Ames. I think it's still the 3rd largest computer in the world. We go back and forth, people leapfrog us. The military, of course, has the 2 biggest ones. Dr. Warden, our director, says that this is the biggest peaceful computer in the world. So, and it sits there, as you know. We had one called Columbia just before it. Next chart. I said people. Now, these are people I worked with, I find very, it was a remarkable experience to be able to work for these people. This man right here, again, since you're in the computer world, you probably have never heard of him. He developed a swept-back wing. He was a researcher at Ames, and for the first time ever, airplanes were flying with unswept wings. He said, if you're going to go fast, particularly up to Mach numbers of 1, which is the speed of sound, and beyond, you better start sweeping the wing behind the so-called Mach cone. And he was laughed at for a number of years. Finally, he proved it in a wind tunnel. And a man named Busemann, Adolf Busemann in Germany during the war, was doing exactly the same thing. And they didn't know each other. They didn't know they were doing it. So both of them have to be given credit. But after the war, they became very good friends, and Bussmann ended up at the University of Colorado. This man, another remarkable person, Allen, as you may have heard, he's the man who developed the blunt body concept. The blunt body concept is what's used on every vehicle that goes into any planetary atmosphere, including the Geminis, Apollos, the Mercuries. I'll talk a bit more about that. As a young engineer working with him, we kept making airplanes thinner and sharper to go faster and faster. He said, no, if you want to come in really fast, like entry speeds, and he'd been studying meteors, you better make it blunt so the shock wave will essentially dissipate the heat and take it away from the vehicle, as opposed to making it sharper and sharper, because it's going to burn up. You know, the sharp edges are going to burn up. So that became the design for every international spacecraft that goes into any planetary atmosphere. This is the young fellow you may have heard of since you're in the computer world. He started our computational fluid dynamics work at Ames, and therefore small size and bigger computers. Dr. Vincenti, who was Mr. Vincenti, actually, keep calling him doctor. He was my first boss, and the first man who did a lot of the supersonic analysis for aircraft, fighter aircraft. In the 47, 48, 49 time frame, he was very active. He later went to Stanford as a professor. He's now emeritus at Stanford, sending back young engineers to us, even though he's retired. Same way with Dr. Van Dyke. Interesting, Van Dyke came to Ames in 48 or 49. He had a PhD. He was the only one who had a PhD. And Allen would introduce everybody in the room as Dr. so-and-so and so. And Milt would say, my God, does everybody in this place have a doctor's degree? No, nobody had a doctor's degree except Milt. But these people were instrumental in starting the basic work that's kept this center going for, well, 70 years. Next chart. When we started at Ames, we were supposed to be a high-speed flight research activity. Therefore, we started building wind tunnels. And if you've ever been to Ames, you know we built on the order of 15 different wind tunnels, different sizes, different speeds. But we also got into flight research. We'd probably test flight research every aircraft that the military had at Ames for them. This is the big wind tunnel at Ames with the swept-back wing in it. This is George Cooper, and I'm sure all of you are. Peter must particularly know George. He retired about 20-plus years ago and went back home to Saratoga, California, and built a vineyard called the Cooper Garrett Vineyards. Very nice wines if you hadn't had it. Good tasting room, so if you're ever in Saratoga, you ought to go see it. But he started out and developed what's called a Cooper-Harper rating scale. This tells you how well an airplane can fly. You can test it in a wind tunnel all you want to. You can put it on the simulator all you want to, but the pilot's the final judge of how well it can fly. So he had a scale that was developed. It's used all over the world today. So these people started many things that other countries picked up. Next chart. I better speed this up a bit. This is somewhat closer to your era, your areas of interest. These are the folks who really started us out in computational fluid dynamics and helped us build the big computers that we now have at Ames. You may know some of the names, you may not. But as I said, I want to pay tribute to these folks who started this business early on and had the concepts to build computers and other facilities, which I'll touch on as well. Dean Chapman had an interesting career. He was a computational fluid dynamics guy. He got interested in tektites and where they came from. So he went all over the world collecting tektites. Tektites are meteorites that succeed in getting into the atmosphere without totally burning up. Had a great collection of them. He picked them up mostly in Southeast Asia and in Australia. So he evolved from a CFDer in aerospace into a space CFDer for entry vehicles. Next chart. Flight research, as I said, these are some of the examples of the old airplanes, which most of you won't recognize. This was the F-4D. We had the P-80. All the early research aircraft that the military flew, we tested starting back in the early 40s. This one is, of course, if it's there, where tilt rotor. This is one of the more recent versions. The tilt rotor is a vehicle we developed at Ames. The Marines picked it up, and it now is flying in Iraq and other parts of the world. It's got 2 rotors. It can take off vertically. The rotors actually tilt. That's why it's called tilt. They tilt forward, then it can fly at like 250, 100 knots, 250, 300 knots. So it's very effective, and it can carry something like 20 or so soldiers and some equipment. So that's another place we've been in business for years. Next chart. A natural evolution from flight research and wind tunnels is how are these airplanes going to fly, and how can we check them out before we fly them? Okay, so we get the aerodynamic data from a wind tunnel. We put it on a computer. The computer, like the vertical motion simulator, which is 6 degrees of freedom, can simulate any vehicle you want to put the right aerodynamics into. It can simulate a helicopter, it can simulate a space shuttle, it can simulate a fighter. And astronauts all train on this when they come up. It's a 6 degree of freedom. 3 people can get in the cab, and they can really feel like they're flying the shuttle. And the nice thing about it is when they crash, they can walk away from it. So that came naturally out of our flight research and wind tunnels data. Next chart. Advanced computing came naturally for a different reason. Before the 70s, ILIAC, we had one of the first parallel processors in the world that we stole from the University of Illinois, or one of our directors did, and it's for doing computational fluid dynamics. All the way through this whole era, we developed faster and faster computers until we got this one here. Doing computational fluid dynamics, now we use the computers for much more than that. We can model climate. We can model, you know, when the shuttle had problems and the first time when the foam came off, hit the leading edge, damaged it badly, so the shuttle did not succeed in flying back to Earth. Now, in real time, every time a shuttle is launched, we bring this computer up. So it can calculate in real time. If something comes off, it can calculate the velocity and the mass of it. We have to judge to see what the impact for my characteristics and the damage might be. So it's a real-time lifesaver for the space shuttle. Next chart. This is kind of, we built up a number of these things. Most of you probably aren't familiar with wind tunnels per se, but basically it's a closed-loop circuit, generally a closed loop with a compressor in it. So it blows air past a model. The model has inside it a balance which measures all the forces, drag, pitching moment, what have you. And these are the ones we built. We built low-speed wind tunnels. We went on up to larger wind tunnels. And the biggest one in the world, which is the 40 by 80 by 120 over here, that is the biggest wind tunnel in the world. And these sizes I'm talking about, these sizes, means the diameter of the test section, having nothing to do with the length of the wind tunnel or anything else. It tells you what size model you can put in the wind tunnel. In addition to wind tunnels, though, we decided we need other kind of vehicles that could go even faster. If you build a wind tunnel and try to go Mach 10, the air tends to freeze up on you. So you can't go much faster than 10 or 15 Mach number. If you want to get up to Mach numbers of 25 or 30, like entry speeds back into the Earth's atmosphere, we built ranges and we built arc jets. The arc jets are vehicles that you can put an enormous amount of heat into. So you can look at the heating rate of a vehicle coming back from the moon or the Mars into the Earth's atmosphere, which is about 11, 12 kilometers per second, very high. As an aside, we also helped develop a spacecraft to go to Jupiter back in the 70s. The entry speeds into Jupiter are about 4 times Earth's. Earth's is about 11 kilometers. And the heat goes up as a cube of the velocity. So Jupiter space probe was almost half heat shield. But these facilities were developed both for aircraft and spacecraft. The next chart. I use this chart sometime, and it's the only chart I use to give talks. I try to put on one chart 70 years of what we've done. I've touched on a lot of these back here, like the swept wing, the blunt body. The lifting body was another thing we did back in the 50s, and it actually turned out to be the precursor for the space shuttle. There was a great debate going on when the shuttle evolved from Apollo as to whether it should be a a non-lifting body or a lifting body. Because of some requirements that the Air Force was decided it should be a body that has a lateral range to it, as opposed to just coming in and parachuting down. So the Space Shuttle came out of this lifting body work. Tilt rotor I've talked about. I'll go to the current period. We talked about the computer. We talked about the biggest wind tunnel. Out here now, we've got three things going. SOFIA, which is flying now, and science will start later this year, is a high-flying infrared telescope in the 747 SP. Kepler, which you've probably read about in the last week or two, is a spacecraft we just launched to look for habitable life, planets that might sustain life in other galaxies. We had a real important event. It was launched about 3 weeks ago, but day before yesterday, the telescope blew the dust cover. There was a dust cover to protect it when it was launched, and it successfully got rid of that dust cover. So now the telescope can start looking and start gaining data. It'll probably be flying up there for about 3 years, trying to determine whether or not these other planets may have water vapor. Of course, you look for water. And it does it by an occultation technique. If the planet goes in front of the star just briefly, you see a diminishing in the light output. That's the way we'll detect the planets. L-Cross, which is another fun one coming up, it's going to be launched now about June 2nd, I think. It's a little piggyback vehicle that's going on a spacecraft going to the moon. You should be interested in this from your Google moon stuff. It's going to release the spacecraft when it gets into orbit around the moon. A piece of that spacecraft will crash into a crater while the little one orbits and flies through the plume, hoping to pick up some information on what the content of that plume might be. And that's coming up in June. So these three things all are very important to us this year. May depend on whether we keep our jobs or not. I don't know. Well, I hope they'll all be successful. One of them has been, Kepler has got a good start. Next chart. I've touched on these two some. I've got a series of charts for Ames contributions to aero stuff, and I'll show them briefly. I've mentioned flight research. I mentioned the Cooper rating scale. Actually, in the short-haul vehicles that we developed here, the swept-back wing, this is one I worked on myself. Conical camber is just something you put in a wing to make the drag less. It was put on the B-58 bomber. Anybody ever hear of the B-58 bomber? It was a beautiful delta wing airplane. And the one thing, I was a project manager in the 6x6 foot wind tunnel on it. One thing I remember about, we used to have a Air Force colonel came to visit. He was a project manager. He brought these two little boys with him. One was Ron and one was John. His name was Colonel Duchendorf. And 10 years later or so, he came and said, I'm going to go hear my son sing. Do you want to go with me? Turned out, he said, but he's changed his name to John Denver. So it's no longer Duchendorf. So that's how we got to meet John Denver. But that's why you get to meet a lot of people in this business. In fact, I got one at the end that shows some more interesting ones. Next chart. We'll go quickly through these because I've talked about some of them. Air traffic management is something I haven't mentioned, actually. We've been in this business since back in really the 60s, working with the FAA to try to help the flow through both on the ground and in the air. We developed algorithms. We passed them on to the FAA. They put them in place to help the air traffic management system. That's been going on since the late 60s, and it is still going on. And I put a person's picture on him. He kind of started the whole business, and he's still working, actually working for the University of California, but for us. The next chart, it's air traffic. This is Mercury and Gemini. I told you we had ranges. We fired models of the both Mercury and the Gemini capsules in these ranges to determine their characteristics. This happens to be a picture of he was the vice president then. That's Johnson, if you don't recognize him, when he came to visit. And this is a gentleman I've talked about before on his trajectory entry physics studies. Next chart. I'll do this. Apollo. I've mentioned Harvey. He developed a blunt body, which made Apollo possible, really, in the form that it took. But we also had some other interesting contributions to Apollo. Our people at Ames developed the guidance system on Apollo. Now, it was very critical because when Apollo came back from the moon, it had to go within a narrow, I call it a window, but if it hadn't gone right into the right spot, it would have either skipped out and gone beyond the Earth or it would have dived in and burned up. So this was a very critical design. It was passed on to Lincoln Labs, and they built the guidance system. Lunar surface magnetometer, we had some scientists at Ames who were working on the science of the moon even at the time in the 70s. And they put a magnetometer on the surface of the moon on 3 different Apollo configurations. Life sciences, we got into the business in the mid-60s, and I'll go into that with another one. But these are the kind of things we did with Apollo. We actually tested, if it's a picture of it here, the chute, the parachutes in the big wind tunnel. That big wind tunnel has come in very handy for a lot of things other than helicopters and aircraft. We tested the MER parachute, the little MER, and it failed. 10 months before launch, it failed. They had to go back and redesign it. And it was the only place in the country, probably in the world, that you could get the right dynamic pressure that exposed the forces on that chute. In fact, yesterday, we just tested the MSL parachute. Didn't fail, but it's really incredible. This chute's huge. The 80 by 120 test section is also huge, if you haven't seen it. But it opens up and deploys completely as though it were coming down in the Martian atmosphere. And it worked. So we're okay there, I think. Next chart. This is Space Shuttle. I've mentioned again the lifting body. This gentleman is the one who helped develop the lifting body. And of course, we tested the Space Shuttle for 15,000 hours in the wind tunnels before we ever designed it and flew it. We tested it in the big wind tunnels. We tested it in the supersonic wind tunnels. We tested the configuration. If you recall, the shuttle is transported back and forth on a big 747. Well, there was a worry way back that when they drop tested it at Dryden, would it separate smoothly and easily? Or would it get sucked back into the 747? Well, we tested that in the wind tunnel and had 2 stings that went into the back. It actually separated the 2 vehicles and showed that it could indeed be done right. But the pilot on the 747 was still kind of shaky about it. But at least he believed the data and it worked. Okay, next chart. Astrobiology, we got into that business with a guy named Dr. Klein in the mid-60s also, looking, and it turned out that we have a series of fantastic people working in the astrobiology community. Not the least of which Dr. Barry Lindbergh, who was a Nobel laureate, who I think he came over here a couple of times when he was visiting us, when he was working with us. He now is retired and helping us with the Lunar Science Institute. But that is another discipline that we started in the mid-60s that we still got going. The next chart. Similar with the lunar exploration, I've talked about it. I've talked about the work we did on Apollo. It's another little spacecraft we launched in '98 to look for water on the moon again and managed out of Ames. This one I've talked about already. So in the future, we're looking, most of the wind tunnels and the ArcJets now are devoted to looking at the Orion and some of the new Apollo shapes, which are just large Apollos, but what the characteristics are. In the Markman range, we can test between about 1.5 and 3.5. The next chart, Mars exploration. This is one of your interests, I think. This gentleman, again, is the one that had developed the experiment for the Viking spacecraft, which landed on Mars in '76. We had 2 of them that landed on Mars. We did not manage that project. It was managed by Langley, but we had the principal investigator on it. And the MERS as well, which, of course, as you know, lasted much longer than we anticipated. Here's a picture of the chute I mentioned being tested in the big test chamber. They unfurled it just as though they were coming down through the atmosphere for both MER and MSL tests. Interesting, the Air Force runs that for us now, and they were kind of shocked to find that the first test the Air Force had in the wind tunnel had nothing to do with airplanes, but the Mars parachute. Next chart. Planetary exploration as well. I've talked about most of these. We've had spacecraft. I didn't mention the Pioneer spacecraft. I should have. Back in '71, '72, we managed a small spacecraft that went, well, '75 it went to Venus. But the first one that was launched and it's the first man-made object to ever leave our solar system. It was launched in '71, went beyond the planet Pluto some years later. We thought it would last about a year. We ended up having to turn it off about 30 years later. It was still beeping faintly from beyond the orbit of Pluto. No interesting data, no useful data. But that was one of our first excursions into project management, which we are currently working fairly heavily in. Next chart. Here we go now. This is kind of where we are today in terms of our active vehicles. This is the big one. If you've not been there, you probably should try to get a chance to come around and see it. It's got the small test section. I'll call it the small test section. It's 40 by 80. It's right here. The big test section is right here, 80 by 120. This is the inlet, which sucks the air into it. It's about an acre in size. And you can put full-scale airplanes or spacecraft in there and test them full scale. The simulator is still working. The unitary plane wind tunnel is just a series of test sections which go from Mach numbers of 1.5 to 3.5. So for the same size model, you can go 1.5, 2.5, 3.5 Mach numbers and get the characteristics. Sophia, I talked about. We have shops there. We can still manufacture things. The supercomputers, the ranges, and the arc jets are still operating. I put this on just for fun because, as you know, we've got 75 years ago, the Macon crashed last year. And almost to the day, this thing came back and we dedicated the Zeppelin that now flies out of the airfield using one of the big hangars, not this one. We have 3 big hangars. So we lease it to them and they let us use the Zepp sometimes to get data, atmospheric data. I think they're advertising now you can fly on it for $199. I've been up to point out historic sites for them. It's kind of fun, very quiet, very peaceful flight. Anyway, those are the kind of things that are happening right now. Next chart. And this is sort of the technical capability. I'll just let you glance at them. From aero to air sciences, high-end computing. We're into small satellite world with Pete Warden, the new director. We've got 2 institutes over there, an Astrobiology and a Lunar Science Institute. They're virtual institutes. So there are universities all over the well, actually all over the world that are part of those institutes. And as I said, we're still working on, for the new spacecraft going to the moon. So we got, I don't think I have a chart on, we have about 2,500 people, about half are civil servants, half are contractors. And the annual budget is on the order of $700 million, which is small for you folks, but pretty good size for us. The total NASA budget of like $19 billion, we get about $700 million of it. Next chart. These are, we've got a research park that some of you are familiar with probably now. When the Navy was here, we had a central 400 acres, which we still have for the NASA site, but they had about 1,800 acres. When they left in '93, they gave the whole parcel to us. So we're making a research park out of it with a number of members. And as you know, we have agreements with Google and others to do certain things on the property over time. We've always been heavily into education. And I should mention this summer, we have an International Space University. For the first time, it's going to be at a NASA center. About 120 kids from all over the world that'll gather there for about 12 weeks and study a special curriculum they've got set up. Most of them are advanced degree people that've got their PhD already. So we're setting up a special place. We can feed them outside the main entry gate, outside of the inner entry gate, the main gate they come into. Over by the big hangar, we've got a place we're going to set up for the kids for the summer. So it's going to be a very active summer with anywhere from 400 to 500 young people flowing through. It may look a little like Google. Well, I would tell people if you're going to eat lunch, you better go early because you're going to not get food if you don't. Next chart. Just got a couple more. This is kind of what, now this is what we think before we get a new administration in, which we don't know what the situation is going to be. This is kind of the way we think we're going to be headed toward the next 10 years or so until we return to the moon on the order of 2020. Next chart, this is one the students like. I like to show this because it compares the Space Shuttle with Apollo with the two new vehicles. This takes people into orbit, the new one, the Ares 1. This takes cargo, and the rest of them all the way to the moon. So we now have two vehicles. The thrust of this one was about 4.5 million pounds. The thrust of this one was on the order of 6. I don't know whether any of you have ever seen this. The most impressive thing I've ever seen was an Apollo launch. I remember the first one I saw, Apollo 8. I like to take pictures, so I took a camera, and it was one of those old cameras that has 20 shots. And before this, it moved so slowly, before it got more than like 500 feet in the air, I used up all 20 shots. But it looked like it was going to fall over. It actually really moves like this. Whereas the solid booster with the shuttle really goes zapping up there. This was all liquid, so very slow. Anyway, that's kind of the architecture for exploration that we see coming. Next chart, I think I just have 2 or 3 left. That's the current exploration roadmap with the next lunar landing, if things go right, about 2018. But the budget's got to be just right. Everything has got to fit just in place for that to happen. We'll see. And the other things that are happening, the lunar lander, there are robotic precursors, of course, before that. And L-Cross, as I mentioned, is the first one in June. The next chart, I tell the kids this is something somebody showed me when I was in Texas. If you stop exploration, they said, did you know the Chinese in 1435 had vehicles that were this big over here on the far right compared to Columbus's vehicle? And had they not got an emperor in place who said, let's stop exploration, this nonsense we don't want to do anymore. And he didn't let them build vehicles more than 3 masts. Somebody said they may have discovered America from the other side before Columbus did. Much bigger sailing vessels, thousands of people on board, and they traveled all over the world in them until they were stopped by this guy. So the next chart led me to this next chart. Oh, this is something I came across at Hoover. You guys know better than I how nonlinear technology can be. This is a Hoover commission, our President Hoover back in '29. They predicted in a linear way these 4 things happening. They missed the really major things that were going to happen in the next 20 years. Even though, having looked at that and being told nothing is linear, maybe you can go a year, but you can't go 5. The next chart led me to saying we're going to do this. We're certainly going to do this in the next 50 years. We're going to do Mars. We're going to do the solar system. The last one, I didn't know what to put on, and I got a 10-year-old grandson who said, sir, why don't you put a quantum gravity machine at the end of the arrow? I said, what the hell is a quantum gravity machine, Zach? He said, Einstein is wrong. You can go faster than the speed of light. I'm going to build it and prove it, and that's what I'm going to call it. So I've been using that on the chart now for 2 years, and he still hasn't come up with a quantum gravity machine. He's not 12 years old. I hope he's working at it. Now the next one, and I think maybe the last one, so this is I do with students. I found it interesting that these people, all of whom you recognize, of course, made their early contributions at very early ages, you know, the age of probably most of you guys. So you can do it if you want to, if you get the right education. You've got the right education, and you're already doing it. The next chart, I was going to leave that one, huh? These are some, I found it to be a real privilege to work with this place, but these are some of the people I got to interface with, you know, and you'll probably recognize most of them. My wife says this is a very self-serving chart, but the students liked it, so I kept putting it in. This is the one who told me it was self-serving, but she liked having her picture with Buzz Aldrin. But these are the folks, you know, these are the first of doing many things, right? Lindbergh, Yeager, so on. Bob Crippen, most people may not know, but he was the first shuttle flight commander. The last chart I've got, I know, this is a fun one. This is a picture in the big 40 by 8 foot one tunnel in 1965. in the big wind tunnel. We tested it, and we set it out on the ramp, and light aircraft flew over and took a picture of it. And the next morning in the San Jose Mercury News, it said, Ames captures flying saucer. Well, this is a VTOL, it really was a VTOL hovercraft. It was a hover with one person in it. And indeed, it was a saucer shape, completely saucer shape, about 10 feet in diameter. So we invited the folks from the Mercury News to come and see it. And the next morning, it said, Ames refuses to admit it captures flying saucer. So we gave up, and that's it. That's all I have. Thank you. Okay, sure. Thanks, Orlando. Sure. Do you have any questions? I'll try to answer them. No questions. Peter? You're bound to have a question.
I got lots. Can you tell us about the development cycles and Golden had the better, faster, cheaper. I think Scott was doing it in the Lunar Prospector before Golden came along.
About the cycle?
Things changed in terms of this speed of progress. So.
Well, I would go back before Golden, though. I think the Pioneer was one of the first faster, better, cheaper spacecraft we did. It was done in the late 60s and early 70s. I think two things were that I remember. One, we had a very capable guy who used to be in the wind tunnels who managed the project, Charlie Hall, the Pioneer. After we sold the project for whatever millions of dollars, and it was probably 60 or 70, the headquarters people sort of got out of the picture. They got out of the way. And they said, okay, manage it to cost and to schedule, and we aren't going to bother you. Report every 3 to 6 months. And we did it. You know, we got it done. When we had a guy who was very capable. He would only have stand-up meetings. He wouldn't have sit-down meetings. He wanted to have project reviews, but he wanted it quick, fast, to the point. He ran a tight ship in terms of the funding. We had a small contractor at TRW, I think it was. And there wasn't a lot of reporting back, but it was also not a very big dollar project, so people weren't too concerned about it. You know, in the late 70s and the late 60s and early 70s, everybody was focused on manned space flight. So the little unmanned vehicles we kind of got left alone. So I think two of the reasons we succeeded in doing it rapidly is we were left alone and we had capable people. Now, I shouldn't say we don't have capable people now, but there are so many loops you have to go through to justify the project, to keep it on track. We have meetings every month on project management, and you have 50 people there, you know, and people from headquarters calling in. So I shouldn't say it's not the right way to do it. Maybe this day and age we have to justify every dollar we spend, but it's certainly not the efficient way to do it. Now, Golden had the right idea, I think, but all three of those together may not work. Maybe two of the three. But you guys know how to do faster, better, cheaper than Golden did, it seems to me. Yes, sir. You don't have to worry about the politicians either. If you let a contract now and it isn't in the right part of the country, you get 3 politicians jumping on you by saying, why don't you do it in Florida or Marshall or wherever?
It seems like the history of manned spacecraft development over the last 30 years has involved an awful lot of fits and starts and stopping projects when they're half done or 10% done.
It's the nature, I think, of the beast now when we change administrations. Everybody wants to get their own oar in the water as to which way we want to go. I suspect we may be in for a little bit of that coming up, so nobody knows how that's going to turn out. But you're right, there are a lot of, I don't know how you justify going over by 2 or 3 on a project, even no matter what it is, manned or unmanned. But I almost want to conclude, and I know it's not right, that the people that we're using aren't as capable as the ones we used to use. Just maybe we don't find the right people, because I know they're there. You know, I got a smart grandson, 2 or 3 of them. But.
Jack, how much is the function not only of the NASA top administrator, but like of the president?
It's not just.
Like comparing Kennedy Like, imagine like George W. Bush in the Kennedy years. I mean, what would his answer be to the Russians?
It's not just NASA. It's the whole system, I think, that's changed and gotten more cumbersome, I think. I don't know how we can streamline it, though. If anybody can, it would seem to me the things we learn from companies like yours ought to help us streamline things. Because you certainly do things in a streamlined way, from what I can tell. And I'm not a computer person. I'm a wind tunnel jockey. Yes?
Didn't you say you met Orville Wright?
I met Orville Wright one time. He passed away the next year. He came, both he and Lindbergh were on the NACA committee, and they used to come to the different centers for their meetings. That's the way it happened. You know, most people think he died in 1900 and 5. I guess it had to be after 1903. Yeah.
You said that the Air Force is running the wind tunnel now?
This one. The Air Force is running the big wind tunnel. We had no, it turned out that we kind of phased it out because we had little use for it, not enough to keep it going. And we posed the question to the Air Force if they would like to pick it up and operate it for us. So that's what they're doing now, yes. So whoever comes to it, the Air Force sort of screens and decides who's going to do who's going to test and what have you. So they're on-site managers for that big wind tunnel, yeah. And we actually, it's not new to us because many years earlier we had the, I guess you call bailed one of our, we have 2 7x10 subsonic wind tunnels, and we bailed one of those to the Army to do helicopter research back in the late 60s, I think. So it's not unique. Yeah, Peter?
I heard a story about when William Shatner came to.
About whom?
William Shatner. Do you remember that?
Yes.
The Star Trek guy?
The interface I had with him?
Yeah.
Well, he came up a couple of times. One time he came in and he was looking for information to write a book about things that were in the Star Trek movie. He said, which ones are real and which ones can never be done? So he had that discussion with some of the folks at Ames. And then I've forgotten how it came up. He said to me, I would like to meet Edward Teller. And I said, well, I know Edward pretty well. Why don't, next time you come up, we'll take you over. And he said, no, I want to meet him today. So I called Dr. Teller, and he said, who is this William Shatner? I said, it's Captain Kirk. Oh, I know Captain Kirk. Bring him over. So we took him over to Edward's house. Just the 3 of us were there. And he said, Shatner walked in and said, I want to know about quantum mechanics and string theory. And Teller said, well, I'll tell you what I know, but you won't understand any of it. So it just took him aback for a bit, but then they got together, and for about 2 hours, they had a very interesting conversation. I have a better one, Peter, though. When I was in college at 17, I invited, you ever heard of Shirley Temple? I invited Shirley Temple to come to my prom. Okay. She didn't come, of course, but she sent a picture, beautiful picture of a 16-year-old. She was 16, I think. I was 18. And years later, well, just 3 or 4 years ago, my wife found the picture. And it had written on there, to Jack, Shirley Temple, sorry I can't come. I don't know who wrote it, probably her press agent. Anyway, so she lives close by, so we invited her to come over to Ames to talk to some students. And she came, very bright lady. She had a good interface on the computer with students answering questions. And I told her about this occasion. She said, well, it's been 60 years, but why don't we have a date now? So let's go out to lunch. So she and my wife and I got to go out to lunch together, 60 years later. She's still living in near Woodside somewhere. But you do get to interface with lots of fun people. Okay? Okay.